Okay. Current slide. And let me go over just the end of the term stuff, okay? Number one, have you done the student course evaluations? Anybody? Good. Lots? No. Okay. Please get them done, okay? You don't have to do them now. You can wait until you see the final. You can even wait until you see your final grade if you want to wait that long, but just don't forget. I know when I was an undergrad, the end of the term came, and when I finished that last exam, it was like an Etch-a-Sketch. Shook it and everything was gone, you know, as far as remembering to do things. So, of course, the material wasn't gone, but the remembering to do things like that was gone. So please don't Etch-a-Sketch it away. Please get your thing done. Now, while we're on that subject, this, obviously, my best class ever. And actually, you are a very good class. We've gotten further in Cal 1 than I have in any other class before. Way to go, team. But, big but here, I've still only received one research paper. Why? And it's the end of the term, okay? So only one person got any bonus points this time, and he got them all. Okay. So anyway, please get your research papers in sooner rather than later, okay? If I get it in after Monday, Monday is fine, but if you get it in today, tomorrow, Friday, or Monday, fine. If it's after Monday, you start losing points. So please get them in sooner rather than later. Okay, test 1, I've still got 2 people who haven't turned in test 1. Okay, test 2, I've got 2, 3, 4, 5 people haven't turned in test 2. Test 3, I've only gotten 2 in, unless some have come in recently. They may have. And test 4, that's the one that's coming up, right? Yeah. So that will be your last test. So none of you have turned that in yet. I don't know why. Okay. But anyway, we'll go from there. Let's see. 2, 3, 4, 5, 6, 7, 8. 2, 4, 6, 8. Got it. All right. Now, there was a question about finals earlier. There was a final examination schedule published a few weeks ago, and I saw it to begin with, just sort of glanced at it and went on. But later, when I was actually looking at it carefully, I saw it was wrong. Okay, so I emailed the dean and said, "Wait, this is wrong. The academic calendar, the administrative calendar, all the calendars say finals going from Tuesday through Monday of next week through Monday of the following week. But you have the finals down starting on Monday." Well, never heard back. But finally, I talked with my boss yesterday, the associate dean. He said, "Oh yeah, she realized she made a mistake." But then thought, since she's already got it out there, she'll let instructors choose whether to give them Monday or the following Monday. So we're not allowed to do that, but I guess she is. So anyway, Monday is our last day of class. So we have class today and class Monday. On Monday, I'll give you your final. You can get it to me anytime this week. Are any of you graduating this term? That's sort of good, okay? That means we'll have you again. But the other thing that it means is that your grades, anyone graduating this term, I have to have your grades in by noon on Friday. So that meant y'all would have to have your graduating students have to have the test in to me by Thursday so I can get it grades in by Friday. But the rest of you, anytime up through next Monday, and because your grades aren't due until Wednesday of the following week. So I think we're okay there. And please do the student course evaluations. Had I mentioned that before? Okay. So let's get started. Sorry we're late getting started. Like I said, it's been a crazy morning so far. In fact, all week has been like this, pretty much. All right, let's talk about integration. Oh, at first, any questions on anything we've covered so far? And folks, please, those that are behind on tests and research papers, get them in, okay? It's already just yesterday, well, this week, this stack is more than double, okay? So I've got tons of grading to do. I'm still working on fall schedule because it's a total mess, but I'm gradually getting it straightened out. Okay, Any questions? All right, integration of even and odd functions. Okay? Guess y'all remember what even and odd functions are, right? Okay? But here's how they start. Even with a change of variable, integration can be difficult. Oh, shame on them for saying that. Okay? Occasionally, you can simplify the evaluation of a definite integral over an interval that is symmetric about the y-axis or about the origin by recognizing the integrand to be either an even or an odd function. Okay, if you're integrating this function here, whatever it happens to be, and it's pretty obviously symmetric about the y-axis, from negative a to a, okay? Now, of course, you would do the antiderivative of whatever this function is and evaluate and then plug in a and plug in minus a. I don't know if you've noticed it yet or not, but plugging in zeros are pretty easy, right? We're plugging in minus a, there you have a minus sign, and it's real easy to make a sign error. Oh, so easy to make sign errors. So, but notice here, if this is indeed an even function, meaning completely symmetric about the y-axis, you can integrate this from 0 to a. 0, I like integrating from 0 to a and double. And there will be your answer. Same answer, less work. For you lazy people, this is a windfall. For those who like to work hard, sock it to it. You know, it won't matter to you at all. But for an odd function like this, and you notice the area above the curve here, line here, is exactly equal to below the line here, guess what that integral is going to come out being? 0. Because this is the positive area, that's the minus area. That's even easier. So if you have an odd function symmetric about the origin, then whatever this area is negated by that area. And if as long as it's from minus a to a, look, that's going to be 0. You don't even have to do a thing to that. Now, if it was from minus b to a, yeah, you still have to integrate, but then you can just do minus b to minus a and save a little bit of effort there. Make sense? All right. Let's see how that plays out. Oh, here's the theorem that states that. Let f be integrable on a closed interval from minus a to a. Okay, they got exactly symmetric there. If f is an even function, then the integral from minus a to a of f of x dx is exactly twice the integral from 0 to a of f of x dx. Usually that's, well, the integration is exactly the same, so you don't gain anything there, but the evaluation is so much easier going from 0 most of the time. But if it's an odd function going from minus a to a, just write down the answer as 0. Because if it is absolutely an odd function, not a neither, but an odd, and it's going from across the thing, that's going to be 0. Every time. Okay? No work required. Okay. So let's evaluate this definite integral here. Okay. Now, of course, with indefinite integrals, you got to get the answer plus c, because you don't know what the limits are. But with the definite integral, we do with it. Okay. So what in the world do we have here? Any ideas? Integral from negative pi halves to pi halves of sine cubed x cosine x plus sine x cosine x dx. Any ideas? Just integrate. We can do that. It's not hard. What you think? What's that? Just integrate? All right, let's do it. What would you do with the first part here? Anybody? The first part, this part right here. What would you do with it? Any ideas? No ideas at all. Say again? Oh, you mean from the whole thing? Then you have a product. Actually, that's not a bad idea. Let's try it. Okay, since you came up with it, we'll do that. Integrate from minus pi halves to pi halves of, I'm going to put it at the end, if that's okay. Sine cubed x plus sine x, because you did say in it, factor out the cosine x. Okay, that's a perfectly legitimate move and actually could be helpful, I think. Yeah. I think it can be. Okay, what would you do next? Anybody? All right, good deal. Thank you. It's been like that all day. Okay. Late work. Okay, what?
Integrated.
Second?
Integrated.
Oh, yeah, it's good. That's what the integral sign means. How do we do that? Just give me something to go on. Had a factoring, which is not a bad idea, so we did it. Tell me what next. What is the title of this section? As you have your books open. By the section, not the chapter, the section. Second? No, not the subsection, the section. 4.5. What's its title? Second? 4.5? Integration by substitution. Hint, hint. Want to give that a shot? Okay. That would go let. I'll even put the U. I'll even put the equal sign. What would you guess? Second? Sin X. I love it. Okay. Whew, I feel like a dentist up here pulling teeth. What's my next step? Then, I'll write the then part. Then, du. It's equal. I'll put the equal sign. Okay. Is what? Cosine x with one other little thing. A d over here requires a d over here too. Dx. Okay. And this is exactly what we've got here. So here's our du. Okay. What would the first part of that be then? U cubed plus u du. Excellent. Now, what would be our limits now that we've changed from sine to u? When sine of x is minus pi halves, what is, when x is minus pi halves, what is sine of x? You have to remember trig. Minus 1. Perfect. And when x is pi halves, what is sine x? Anybody? What is sine of pi halves? 1. All right. Whew. All right. Now what does it look like we have? A little louder.
Definite integral.
A definite integral, yes, we got it, okay. And what do you want to do with it?
Degree.
Okay, how would you do it?
U squared over 2.
All right, we're going to do it that way. That would be u to the fourth, did I hear? Say yes? Okay, I thought so. Over what? 4, good. Plus u squared over 2. Integrate from -1 to 1. Okay? Plugging a 1 in there, what is 1 to the fourth? 1 over 4 plus, and 1 squared is? You can do, yeah, 1/2, got it. And then when we do the minus, when you put a -1 in for u to the fourth, -1 times u is, to the fourth is? Okay, what? -1 to the fourth is +1. You got the minus sign in front, and that would be a 1/4. Agreed? Okay, and when you square -1, you get a, you do? A what? What do you say? +1. Okay, I thought you said -1. I go, what? Okay. Now, what do you think that's going to yield? 0. I can tell we got a bunch of hard workers in here, okay? Because as soon as you did this substitution and got it into this form, what do you notice about both of these? They're odd functions. Anytime you have a polynomial function with only odd exponents, it's an odd function. Guaranteed. Okay? If you have a polynomial function with only even exponents, it's an even function. Guaranteed. But if you have a mixture of even and odds, it's a neither. Okay? As soon as you see this, you can say odd function, symmetric, 0. Okay? From the top of the page, that theorem at the top of the page. But we've proved it. Okay, we showed that was absolutely correct. But you see how many places there are to make potential sign errors here? You avoided all those if you saw, oh, that's an odd function. Symmetric, 0. Okay? That was example 10. Okay? Let's see how they did it. Possibly a little shorter than we did, but let's see. Okay? By letting f of x be, oh yeah, that would be it. F of minus x is that. They did the whole function here. The f of x be what the inside was, okay, the integrand. Then they put f of minus x. That's going to be a sine cubed of a minus x, a cosine of a minus x, a sine of a minus x, and a cosine of a minus x. They didn't do the substitution, but when y'all had me factor it out, I said, well, then let's go on and substitute. And then I thought it might be a little clearer. But when you plug these in, what is sine of a negative number? Negative sine of that number. And then you cube that, that would be a negative sine cubed of a negative x. What's cosine of a negative number? Well, cosine is even. This is cosine of the positive. So this would be, I said negative x. This would be a negative sine cubed of x. This would be a positive cosine of x. This would be a negative sine of x because it's an odd function. And that would be positive cosine of x. So you have exactly the opposite. Well, I think they'll write it down. So yeah, they did this. The sine of a negative x is minus sine x. So you cube that, you get minus sine cubed x. Cosine of a negative x is cosine of x. So just write that down. Sine of a negative x is minus sine x. and cosine of negative x is positive cosine x. You do all those plug in, and you get exactly the opposite of what you had here. Exactly the opposite. That's indicating this is an odd function. When you plug in a negative x, if f of x is the exact opposite of f of negative x, it's an odd function. If it's exactly the same as f of negative x, that's an even function. And if it comes out being anything else, it's a neither function. Okay? This is an odd function. So once you determine that, you can write down your answer, and that's minus f of x. F of negative x is minus f of x. That's we just noticed that. And since f is an odd function, because f is symmetric about the origin over the interval from minus pi halves to pi halves, you can apply that and just write down your answer at 0. So we could have done that at the very beginning, but it was not hard to factor out a cosine x, which is good, and then see a substitution. And as soon as you did that, then you see that's an odd function because it's a polynomial. It's harder to see when you have these trig functions. You have to sort of go through that whole thing of substituting a negative x and evaluating. But here is a graph of it, and of course, here's from negative pi halves to pi halves. Oh, okay. This is a graph of that function, not sine. Okay. I wasn't about to do this, but once you see it is done, this is exactly the same as that. When you add them together, one's negative, one's positive, comes up here. All right. Good deal. Thank you. All right. It's been all day that way. Okay. However, because one lies below the x-axis, one above it, integration produces cancellation effect. You get a sum of 0. Good deal. And that was the last example. 4.5 homework exercises. Well, I've assigned most of these. I'm going to do them again. Any of the odds, either 5 or 7, they're both at Calc Chat. 5's at Calc View. Any of the odds 9 through 29, they're all at Calc Chat. 15's at Calc View. Either 31 or 33, both at Calc Chat. 31's at Calc View. Do 35, it's at Calc Chat. Do 37, it's at Calc Chat. Any of the odds 39 to 47, they're all at Calc Chat. 45's at Calc View. Either 49 or 51, they're both at Calc Chat. 49's at Calc View. Any of the odds 53 to 59, they're all at Calc Chat. 53's at Calc View. Any of the odds 61 to 67, they're all at Calc Chat. 65's at Calc View. Either 69 or 71, or both, they're both at Calc Chat. 69's at Calc View. 73 or 75, both at Calc Chat. 73's at Calc View. And 77 is at Calc Chat. 79's at Calc Chat. You can explore doing 81. It's at Calc Chat. Should be, anyway. 84. Okay, I was looking at 83. 84 should be at Calc Chat. I'm sorry, you don't do 83. That's what I meant to say. 83 is a depreciation problem. I'm guessing most of you probably didn't have to do taxes because probably somebody else is doing them for you. But at one of these days you will, and if you have equipment, you will be hoping you can find some depreciation. So that's not a bad problem to do. 85, again, if you're in business ever, which most of you will be some sort of business, 85 is a decent problem. 87, graphical analysis, these should all be at Calc Chat. Rewriting integrals, 89 should be at Calc Chat. Goodness, they keep going on and on. 91 should be at Calc Chat. And any of the odds 93 to 97 are true false. You can do any of those. They should be at Calc Chat. 99, rewriting in that integral again. That should be at Calc Chat. 101's a proof if you want to go that far. Now, if there weren't enough homework exercises at the end of each section, you got plenty more on the review exercises. And again, at Calc Chat, they have tutorial help and worked out solutions for the odd number exercises. So you could do any of the odds if you want to review from the whole chapter. Any of the odds 1 through 7, 9 or 11, 13, 15, 17, 19 through 23, 25, 27, 29 or 31, 33, 35, 37, 39, any of the odds 41 to 45, 47, 49 or 51, 53, 55, 57, any of the odds 59 through 65, any of the odds 67 through 71, 73 or 75. Now there's a problem solving, which is just sort of your fun type stuff if you want to do it, but actually in there you see there's Archimedes' formula is mentioned, okay? That could be a potential paper topic, or just indeed, who in the world was Archimedes and what did he do mathematically? Quite a bit, by the way. Fractional function, I don't even know who fractional was, but he has a function. You can look that might be a potential. Here's Gaussian quadratic approximation. You can write on who in the world was Gauss, quite an impressive mathematician, or his quadrature approximation. You could write on that if that's where your interests are. Galileo is mentioned. Okay, he was quite a scientist. He also had good math skills too. Riemann's sums, we've already talked about. Riemann is, you can either write on his sums or who he was. Just, if you look, there's plenty of ideas for paper topics. Since only one of you have turned one in. Okay, so anyway, let's move on from there. So let's, whoops. I don't know what I just did, but I didn't mean to. All right, let's get into 5.1. This is bonus, basically. You need to know this, but this book, I didn't realize it when we first ordered it, is calculus. It doesn't say with early transcendentals. So therefore, they take the transcendental functions and put them in one chapter by itself and not in where it belongs. So you're doing them when you differentiate and you do them when you integrate. They just leave them out there and then put them in here. So what we're going to do is get as much of this covered as we can, because you'll need this for Cal 2 and Cal 3 and for the rest of your life. So let's go from current slide and get as much done. It's pretty simple stuff. Some of it will be a review of pre-calculus, okay? So logarithmic, exponential, and other transcendental functions. Let's start with the natural logarithm, which is pretty interesting because most books start with exponentials, okay? But this one's starting with natural logs, okay? Either or. So we'll develop and use the properties of natural logarithmic functions. I'm going to try to go through these pretty quickly because you should basically already have a decent understanding of those. We'll understand the definition of the number e, which is getting into exponential, and then we'll talk about the derivatives of functions involving natural logarithmic functions. Okay. So what in the world is a natural logarithmic function? If you remember the general power rule, if you're trying to integrate x to the n, where n is any number in the world except for 1, would be to take, now they're starting off with integration, which is pretty interesting, okay? If you start with this and raise that to 1 unit, x to the n plus 1, divided by n plus 1, except for one value. What can n not be? -1. Why? The general power rule will give you a 0 in the denominator, which we cannot do, not even in calculus. Okay? So, the important disclaimer, it does not apply when n is equal to -1. Consequently, we have not yet found an antiderivative. No, we haven't, they have, for f of x is equal to 1 over x. That's x to the -1. Okay? Power rule does not work here. In this section, we use the second fundamental theorem of calculus to define such a function. Yay, I can't wait. Okay? It's neither algebraic nor trigonometric, but falls into a new class of functions called logarithmic functions. This particular function is called the natural logarithmic function. And here's the definition of it. The natural logarithmic function is defined by, if you haven't noticed yet, second fundamental theorem of calculus, the way this book calls it. Other books call it part 2 or whatever. Log x is defined to be the integral from 1 to x, 1 over t dt. That we don't have, can't use the power rule, we're going to give it the name log x. Now, this is only true when x is greater than 0. Certainly x can't be 0, okay, because you can't put an x to 0 down here. And if it can't be 0, you can't integrate from, well, if it were 0, okay, if it were 0, then, well, you can't do it, number one. So you can go up to 0, but close to it. But you see, anything between 1 and 0, this is a backward integral, and you flip it and make it a minus. What that tells you, or you don't know it tells you that, that means anytime you're between 0 and 1, the natural log is negative. Okay, you probably can't see that yet, but that's going to be true. Okay? Now, you can't equal 0, so you can't go anywhere beyond that negatively. Okay? Anywhere. Okay? Now, anything past 1, then this is, basically, what would it be when x is equal to 1? What would that integral be? Really skinny, going from 1 to 1. What's the area under that curve? Whatever that curve is. You know what that curve is, like this. And from 1 to 1, what's the area there? 0! Because you have no width there. 0 width. You have a height, but you don't have a width. Okay? So that's going to be 0. So it's negative between 0 and 1, not defined at 0, negative between 0 and 1, 0 at 1, and then positive from there on. The domain of the natural logarithmic function is set of all positive real numbers. That does not include 0. It can't be 0, and it can't be negative. So a natural log of x is only, you can only feed in positive numbers. Okay? So, there's our definition for log x. Sort of interesting the way this book approaches it. That's just it. They define it that way. From that definition, you can see that log x is positive for x greater than 1, negative when x is between 0 and 1. It can't be 0, okay? And at 1, it's 0, okay? Because then you have the, if you're integrating from 1 to 1, you're integrating that little line right here, and it has, ooh, let me go and get my pen set up. That line right there, and that thickness is 0, okay? So yeah, this has a 0 area. Anything, the area here would be positive, but you see, if x is negative, if x is less than 1, greater than 0, then this thing, you flip over and negate it, so that then gives you a negative area here, 0 area there, and positive area from there on. Okay. Does that kind of make sense? Okay. So what they're saying here for x greater than 1, wherever your x is here, you have a positive area here. When x is between 0 and 1, then this is a positive area, but you see your integral is 1 to, say, 1/2. 1 to 1/2, you'd have to make that 1/2 to 1, but then you negate the integral. So that takes this and makes it a negative value. And that is indeed what's happening there. So the area then flips to be negative. And it goes to negative infinity, by the way. As you get x closer and closer to 0, that just gets more and more and more and more negative. Slowly, but still getting more negative. So the range here, if you got to 0, it would be negative infinity. We can't ever get to 0. So it's very, very large negative number. Limit b. And there's no limit here either, by the way. That gets closer and closer to 0, but never becomes 0. So your area under there is infinite. To sketch the graph of y is equal to log x, you can think of the natural logarithm function as the antiderivative of this differential equation. Okay? All right, here's what they're saying. This is, they have a name for that. I can't ever remember what it is. Sort of like a slope display. If you plug in an x here, anything between 0 and infinity, this is always positive. So your slope here is always positive. But as x is very, very, very close to 0, it can't be 0, very close to 0, this is an extraordinarily small number. Like, let's talk 0.1. So that slope would be 10. 0.01, that slope would be 100. 0.001, that slope would be 1,000. So you're almost vertical. You would be vertical if you could get to 0. You can't get to 0, so you're getting closer and closer to vertical. So this is very steep here. And then here, when x is equal to 1, the slope is 1. That's exactly a slope of 1 there. And you're at the value 1, 0 there. And then anything beyond that, the slope is decreasing, 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 but never reaches 0. So your log function, that's how it looks. The value is 1, 0 here, very steep slopes for negative values here, always positive slope. Well, that's always positive. And they get less and less positive from then on, but still always positive. Does that make sense? All right. There is a computer-generated graph called a slope field. That's what they call it, slope field or direction field. Two names for it, showing small segments of the slope of one of their x. The graph of this is a solution that passes through point 1, 0. That's a bizarre way to show you the graph. It is. To me, much better to have started with the exponential function, and then this is the inverse of that. That makes, just, you don't have to do slope fields or direction fields or anything else. It comes out of it. So that's why I'm surprised they don't start with the exponential function. Okay. We'll get there, though. The next theorem lists some basic properties of the natural logarithmic functions. Natural logarithmic function has the following principle. As we said before, the domain is from 0 but never reaching 0. That's why you have the parentheses there, to positive infinity. 0 but not counting 0, positive infinity. The range is from negative infinity to positive infinity. Takes a long time to get to positive infinity. Of course, it never gets there, but because it's going up so slowly toward the end, but it's always increasing. And the graph is concave downward throughout its life here. Always concave down. Always. Okay? No inflection points, nothing. Okay. 3 properties of the graph of the natural log, or of the natural log functions. Okay? Now, using that definition of natural logarithmic function, you can prove several important properties involving operations with natural logarithms. If you're already familiar with these, you'll recognize these properties listed as characteristics of all logarithms. All logarithms, not just natural logarithms, all logarithmic properties. A and B are both positive numbers. They've got to be. You can't take the log of a 0 or a negative number. And n is rational. Okay, that means it's ratio of 2 integers, with the bottom not being 0. Then the following properties are true. The log of 1, we've already seen, is 0. The log of 1 is 0. Okay. First property. And this is true for any log. If this is a log, if it's a base 2 log, any log of 1 is 0. Okay? The second one. I bet you Bill remembers this, but probably none of the rest of you. Anyone ever seen a slide rule? I know what I'm talking about when I say a slide rule. Bill does, don't you? Yes. Okay. Back before there were calculators, and guess what? There was a time, way back in history, before there were calculators. Okay? Before my sophomore year in high school, in college. That's the first time I saw a calculator. Okay? And before that, this was at a physics class. I think it was right after Christmas, so it was winter term. In walked two guys strapped on their belt, a calculator. We had heard about them, but none of us had ever seen one in person. And all of us had our slide rules strapped to our belt. But here came, and all of us, as a group, about 200 in the classroom, went, oh, there goes the curve. Okay, because they had calculators. We had slide rules. What slide rules did was make the multiplication, division, and raising powers of big numbers relatively easy. Always approximate, but relatively easy. And this rule right here is what did it for you. The log of this one of the rules. The log of a product is the sum of the logs. Okay, the log of a product is the sum of the logs. If you had to multiply two enormously large numbers, exponents and all that kind of stuff in it, then, or even just big numbers, lots of digits, you could usually get maybe 3-digit precision with it. And what you did with the logarithm, you found on a log scale the first number. Slide the slide over to that, okay? And then, that's why it's called a slide rule. It had a centerpiece that slid. Put your cursor there. It was a little bar that went across. It had a strike down the middle, okay? And then find the second number on the part you just moved, and then read on the top scale what it was. What you did, you added those two logs together. And then what you read off the scale was the product, okay? It was a godsend back before there were calculators. As soon as they got calculators, it was antiquity, okay? Okay. No one used them anymore. I'm not even sure I could find one anymore. Now, if that's true there, now remember, n is a rational number, okay? Actually, I think it works for irrational numbers as well, but the log of a base raised to some power, bring the power on the outside and multiply it by the log of the base. Man, that makes it so much easier to do, okay? You have to know what the log of that base is, but then it's just a multiplication. So here's how I look at it. Logs do this for you. They lower your level of operations by 1. If you think of adding and subtracting as being the easy things down here, then above that is multiplication and division, and above that are powers and roots, okay? What a log function does is drops at one level. It changes multiplication to adding and subtracting, or multiplication, division, adding and subtracting. And it changes the power to multiplication. See right there. So it drops at one level for you. And we get our first X chromosome ready to go. Okay. Ayana is here. Right? Yeah. Okay. Make sure I looked properly when I tried to clean that up. Okay? And then, that corresponding to this, the log of a quotient is the difference of the logs. Okay? And so log of a product is the sum of the logs, log of a quotient is the difference of the logs, and log of a power is a multiplication of that power times the log of the base. Okay. Those are your logarithmic properties. If you got to that in pre-calculus algebra, old hat to you, right? Or high school, wherever you may have hit it. All right, so let's do a few. Log of 10 over 9. Well, they do it for you. Okay, let's pretend they didn't. What is that? You didn't. You weren't paying attention anyway, were you? What is that? Log of 10 minus the log of 9. Now, frankly, I don't know what log of 10 is, nor the log of 9, but I've just changed a division into a subtraction, which typically is a little easier. So let's see if we do that. Oh my goodness, what in the world is that? Log of the square root of 3x plus 2. What would be the first thing you would think of doing to this? We did it in differentiation. We did it in integration. Whenever we had a radical, what do we change it to? Exponent. So what would that be in exponent words? Language. To the 1/2 power. Ah, that's what they did too. And then where would they take it? Oh, they haven't taken it yet. Okay. Where would you take it now? That would be 1/2 the natural log of 3x plus 2. Now, they have introduced a variable here, and they've not warned you adequately. Okay? But really, in this case, you're still okay. Because for this to make sense, 3x plus 2 must be for square root.
Positive.
Yes, or at least non-negative. Okay. But it could be 0. So we should say, for this to make sense, you would have to say x greater than or equal to blah, blah, blah. But then you take out the equal sign, because once you take a log of it, you can't take a log of 0. So it's kind of okay because it was all right here, but really when you're doing this in real life, you put absolute values here to keep that from ever being negative. Can't keep it from being 0, but you can't keep it from being negative. So this can never be negative because originally it couldn't have been negative. Okay? Let's see if, yeah, I need to erase mine. I thought maybe they juked down just enough that I could leave mine up there. But that's exactly it. 1/2 the log of 3x plus 2. Now, was there one of the rules of logarithm that dealt with sums? Properties of logs? No, and don't make up anything. They deal with products and quotients and powers. They don't deal with sums and differences. So don't ever make up any ones for sums and differences. You can't. Okay? And since that, the next operation in line is a plus, nothing else you can do. Okay? That's as simple as you can make it with the properties of logarithms. All right. Listen. What would that be? Log 5. Perfect. Okay. And again, you're just assuming here that x cannot be 0. Okay? And x cannot be negative. Okay? As long as that's okay. But you see, you have to assume it here, and then same thing goes there. X greater, x positive. Okay, just assume that. And that one, that assumption isn't even quite adequate there either. But this one it is. Oh, I forgot to do this. You can split this up. Log 6 plus log x minus log 5. Sorry, I wasn't paying attention. So focused on the domain. So you see, that's still a product. Can't do anything here because that's a sum. This is a product. You can break it down a little bit further. Okay? All right. Good deal. Any questions? Oh, here's one more. What would that be? Next step. Do one step at a time. Squared minus the log of that denominator, right? Which is that. Now, can we go any further? Please say yes. Okay. 2 times the log of x squared plus 3 minus, and here if you need to take an extra step, do the, well, what you tell me. ln of x. Okay. If you're going to do that, be sure you put this in parentheses or some sort of grouping symbol. If you're going to make a plus, Otherwise, you're going to get a sign error here. Okay, plus. Next.
X squared plus 1 to the 1/3.
Oh, okay. I think you meant that to be a log of it, right?
Oh, yeah.
Yes, I thought so. Okay. Log of x squared plus 1 to the 1/3 power. Got it? Okay. I even put the right symbol there by mistake. Okay. Can you do anything else on the first one? No, because of that plus sign there. Okay? Can't do anything else there. So this is 2 log of x squared plus 3. Now, earlier I said, be careful, make sure that x can't be negative. I mean, the log can't be negative. Can that one ever be negative? No. Okay, so you don't need to think about absolute values on that one. That's never negative. Okay. Now, this will be a minus log x. I'm going to just write that down. Okay, but I'm going to distribute my minus sign in here. And what would I have next? Minus, I got it, okay. 1/3 log x squared plus 1. Okay? Anything you can get to make this any simpler? No, because of the plus. Okay? Now, I think we beat that horse pretty much to death. So let's see if that's what they got. Y'all can remember this, right? But remember this. Remember, when you start breaking it down, group it while you're breaking so you don't miss a sign there. School of Hard Knocks is where that came from. See what they did? They first brought the 2 in front. That's good. 2 times the log of x squared plus 3. Minus, and look at that. They even grouped it like I did. They're copycats. Okay. Log x plus log of x squared plus 1 to the 1/3. Or you reading the book. Okay. And then this was 2 log x squared plus 3. Nothing else you can do to simplify that. Then you got a minus log x from the first part minus log. Oh, they took an extra step there. Okay, which is fine. So that's 2 log x squared plus 3 minus log x. Nothing else you can do there. Minus 1/3 log x squared plus 1. Nothing else you can do with that one because of the plus sign. All right. I haven't been keeping up in the book, so I don't know if we're skipping anything. I don't think so. Not yet. Okay. All right. Because I hadn't turned the page, the Theorem 5.1, they did do a little proof here, so I will let you look at the proof. I wasn't paying attention, or I didn't see the proof. We went on to page 316. We've done that, and example 1. All right. So now we're at the very bottom of page 316. Yeah, they just split into 2 sentences, 2 groupings. But using the properties of logarithms to rewrite logarithmic functions, you must check to see whether the domain of the rewritten function is the same as the domain of the original. That's what I was sort of warning you about. Be careful with these, that you don't just make an assumption that now you do all x's or something like that. You have to stay within the limits you have. If I say it like this, but this is what I was getting at. Here's a function, strange though it is, log of x squared, okay? It's good for all x's except x can't be 0, of course. But x can be negative because you're going to square this and you can take the log of a positive number. You just can't take the log of 0. So this is defined here and it's defined there. It's just not defined at x equals 0. Okay? Now, when you do the next step, 2 times the log of x, ups, look at what that function is. It's not defined for negative x's. So this g is not really quite the same as that. that's just this branch of it, okay? A little bit similar to, but not quite the same thing, of what we were doing when we were doing one-to-one functions, type thing. You might only can deal with one branch of it. If this is a parabola, that's not one-to-one. This branch could be a one-to-one. That branch could be one-to-one. This isn't. Well, when you do your operations here, you lose a branch, just like you did when you're doing, not the same thing as doing one-to-one functions, but it sort of has that same kind of feel to it. So for instance, the domain of this is all real numbers except x equals 0, where the domain of the second one is only positive real numbers. Still not equal 0, but you can't have negative in there. And that's why I was saying this was okay, because that's always positive, but when you get here, you'd have to put absolute values around it to give you this branch over here. Okay? So that's why, in this case, the absolute values would have allowed you to do this branch here. So maybe that's what they're going to get at here. Let's see. No, they don't. they leave that out. So that's one reason they can't put in the absolute values later. All right, let's look at the number e. Do y'all think of e as being a number? Quite often we think of it as a function, the exponential function. E to the x is the exponential function. Actually, what that is raising the number e to some variable power. Okay? Just like 7 to the x would be a function. But 7 is a number, well, so is e. Okay? Anyone know what e is? No, 2.7, blah, 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 blah. Irrational number, just like pi is irrational. No pattern to it from there on. It's an irrational number, e. Okay? It is likely you have studied logarithms in algebra course, maybe, okay? There, without the benefit of calculus, logarithms have been defined as in terms of a base number. Now, these are the log logs. For example, common logarithms that have a base of 10, they're common because we have 10 fingers. I think that's the only reason we talk about base 10. Because when you got up to counting on fingers and got more than that, we just had to, okay, there's one 10 and then there's another 10. When you use them all up, you just had to go somewhere else. That's why we use a base of 10. So the log base 10 of 10 is 1, okay? If you studied this in any other context, you're probably used to something like that. Because what you're saying here, this is your base, and with this as a base, what? I'll let them get to it. The wording is difficult to get it absolutely right. We'll come to it in a second. What's that?
If you want to raise it to 0, that exponent would be 1.
Right, exactly. Okay. If you were trying to raise it to a power to get this answer, your exponent has to be 1. This base to what exponent gives you that value? That's what I'm trying to say. That exponent would be 1. I was trying to say it without using exponents because we haven't quite gotten there yet, but I couldn't think of a way to do it. So that's exactly it. The base of a natural logarithm is defined using the fact that natural logarithmic function is continuous, is one-to-one, and has a range from -infinity to infinity. The base for the natural logarithm, okay, has those three characteristics. In fact, it's a continuous function, one-to-one, and has a range of -infinity to infinity. So they're going about this pretty much backwards from what I would have done, okay? So there must be a unique real number x such that the log x, the natural log x, not the log log, the natural log x is 1, okay? That number is denoted by the letter e. The sad news is it's an irrational number. It can be shown that e is irrational, okay, has the following decimal approximation approximately equal to 2.71828. Now it looks like it's going to be a repeating decimal there, doesn't it? Look at that, repeating, except you get here and it doesn't repeat. Okay, so close to having 4 digits repeating until you got here, and then you didn't have 4 digits repeating anymore, and it never even comes close again. Bizarre but true. Okay? Irrational number. Keeps on going. Okay. That's why they put approximately there. Okay. No. Everything they're saying here has really nothing to do with that yet, but we'll get there. Okay? Except that, yeah, it did. This thing right here. Because how we defined the logarithm was from 1 to e, what would give you an area under here of exactly 1. Okay? That would be the number e. Strange way to look at it, but that's absolutely true. Okay? And that would come out around 2.7, blah, 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 blah. So here's the definition of e. The letter e denotes the positive real number such that the log of e, which is, by our definition before, the integral from 1 to e and 1 over t dt, that log of e is 1. Okay? Once you know that log of e is 1, you can use the logarithmic properties to evaluate natural logarithms of several other numbers. Okay? And that does give you an edge. Okay? Because we can now do things we couldn't before. Not easily anyway. All right. Now this is using, like they said, second fundamental theorem of calculus to define all this, which is a perfectly good, now I guess a very rigorous or elegant way, some sort of way of doing it. Frankly, I would have done it more differently, but we'll get there. Okay. For example, by using the property that the natural log of e to the n, of course, would be n times log e. What's log e? 1. So that is n. Okay? So you can evaluate log n for various values of n, and that's shown in this graph here, and this will give you this is sort of assuming you know what E is. I guess that was the base assumption here. And once you do, then it's real easy to get the natural log of it. Okay? And so the natural log of, if x is equal to this, 1 over e to the, that remembers your 2.7 blah, blah, blah. But guess what? Your calculators all, if you got any kind of calculator, it has the e key on it. And do e to the 1, and you'll always get that 2.71, 2, blah, 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 blah. You'll always see that number pop up if you do e to the 1. So you do 1 over e to the cubed, and you'll get a number approximately equal to this. 1 over e squared gives you a fraction of that. 1 over e is a fraction of that. E to the 0, of course, is 1. And I guess this vertical line here means that's exactly 1. Not rounded, exact. I'm not used to that. No, I think the typesetter just put it in there. It's not in the book this way, so I'm not familiar with that notation. I think that line should be there. And of course, e to the 1 is 2.718, blah, 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 blah. Okay, e squared is going to be the square of that. So, the log of each of these numbers, which are approximate, because except for that one, these are all irrational numbers, by the way, except for this one. And the log of those are perfectly fine numbers, e to the minus, because the exponent here is e to the minus 3, e to the minus 2, e to the minus 1, e to the 0, 1, 2, so on. Okay. So that's how you plot your log curves if you want to. The calculator also has the log key on it, so I don't see the advantage of this. So that's exactly right. Okay, the logarithms shown in the table are convenient because the x values are integer powers of e. Most logarithm expressions, however, best evaluated with a calculator. Well, guess what? To calculate those numbers, you have to use a calculator too. So it's not that this way avoids a calculator, okay? All right. So, just to get an idea, log of 2, use your calculator, okay? If you want to go back and forth with this, you can say log of 2, let's call that some value. You want to give it a value, not a number, but a variable. U, is that what you said? Okay, let's call it U, okay? This implies that, okay, remember how we do our inverse functions? They haven't said that yet, but logs and exponentials are inverse functions of each other. I don't know why they haven't said it yet. That means that, and we haven't gotten this yet either, but that 2 is equal to e to the u. Okay? That's what they were implying by the thing here. 2 is equal to e to the u. Well, no, that's not quite the same, is it? Okay? So that doesn't get you any closer to getting it. Okay? I thought it's true, but it doesn't get you really any closer. So I don't know what they want you to do except just do it on a calculator. That's all. This is really, pull out your calculator and do log 2. Okay? Be sure you've done the ln2. Don't do log2. ln2. What you get? 0.693, blah, 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 blah. It goes on forever. How about log 32?
3.46.
Okay, 3.46, blah, blah, blah. Now, one thing to note, this is 2 to the 5th power. So 5 times this should be that. So go back and do log 2 and multiply it by 5 and see if you get the same thing. Hopefully you do, otherwise get a new calculator. Okay. Right? Okay. So this is exactly 5 times that. Okay? This one, log of 0.1. Punch it in and see what you get. See, we're from the south, we punch it in. You know, other parts of the country, they press it, but yeah, we punch it. Good violence. Okay, it's a negative number because it's less than 1. Remember, anything between 0 and 1, the log of it is going to be negative. And there it is. Okay? Oh, I guess there was a big advantage to having you do that. So anyway, now, I hadn't kept up with my page yet. Okay, here we go. Now it's dawning on me why they defined the logarithm first using the second fundamental theorem of algebra. Because now if you're going to get to the derivative of the natural logarithmic function, once you defined it that way, this makes the rest of it pretty easy. Derivative of the natural logarithmic function is given in this theorem. The first part of the theorem follows the definition natural logarithm function as an antiderivative. Okay? The second part of the theorem is simply the chain rule version of the first part. Okay? Well, I thought they were going to use the second fundamental, but this is it. It's just the antiderivative. If you know that the integral of 1 over x dx is equal to log x, then the derivative of log x, it better be 1 over x. Okay? That's what they mean. That follows from the antiderivative. Now, if you have a log of u, where u is a function of x, and you're taking the derivative with respect to x, then you'd have 1 over u times du dx, which then is just u prime, which is du dx over u, which is sort of interesting. But remember, of course, here x has to be greater than 0, can't be not equal to 0, just greater than 0 to the log. And now the u is the thing that has to be greater than 0. It could be a function of x, but whatever its function is, that has to be greater than 0. All right. Make sense? So now we can take a derivative of a logarithm. We define the transcendental function, and now we're taking derivatives of that transcendental function. Okay. Ooh, let's do this one now. What would that be? Derivative of the log of 2x. Derivative of the log. Oh, it's been a long time, hasn't it? Derivative of the log. 1 over the argument, right? You need to go back a slide. Derivative of the log is 1 over whatever the argument of that log is. Derivative of this is 1 over whatever that is. But then you do a chain rule. Okay? Hint, hint. Okay, we did that one. No, yep. Okay. So what would that be? 1 over 2x times derivative of that is just 2. So 2 over 2x, which again is 1 over x. Now wait a minute. I thought log of x was 1 over x. It is. The log of 2x is also 1 over x. Well, let's see. What is log of 2x? It's log of 2 plus, help me, the log of x, right? The log of a product is the sum of the logs, right? Now let's do the derivative of this. D by dx, that's a d up there, of that thing. The log of 2 is just a number, right? So what is its derivative? 0. So this would be 1 over x. So sure enough, that is right. Make sense? Kinda? Not really. Remember principle of logs? That comes from it. Take the derivative of that thing then, and it has to be 1 over x. So sure enough, it is the same. Okay? How about this one? Whoops. Oh, I didn't do it. So worried about it. Okay? What would that be? Get me started anyway. 2x over what? Plus 1. It's the derivative of the argument. That's one. Derivative of the log of something is 1 over the something times the root of the something. Okay? So it's 1 over x squared plus 1 times the root of x squared plus 1, which is 2x. Okay? All right, you don't need a dx because the dx is over there. Let's see if that's what they got. Bless you. I'm going to erase what I put. Let's see what they got. They say u prime over u, which is sort of what I was saying, which is 2x over x squared plus 1. Now, do you need to put any limitations on the u here? Certainly u has to be positive. But this thing is always positive, right? For all real numbers, it's positive. So there's no limitations on anything here. X could be negative, no problem, okay? U can't be negative because it's x squared plus 2. All right, let's do the C one here. And this, yeah, is example 3. What would this be? Uh-oh. What would this be? What rule would you use? Product rule. So what would that be? How does that go? X, got it. That's the first. Thank you so much. All right, good deal. Just a second. All right. Times 1 over x. I think I can figure out what that is. Next. Plus, I'll do that part for you. Plus what? How'd you get that? Okay, ln x. Okay, I got you already had. So this is 1 plus log x. Is that what you got? Or not? Okay. Product rule. First times derivative of the second, that's what you did here. X times 1 over x, so derivative of log x is 1 over x, right? And that is 1. Okay.
The derivative of the x.
Plus 1, yeah. Derivative of x is 1 times the second, which is log x. It's the first times derivative of the second, plus the second times derivative of the first. The derivative of the first is 1. So you got the log x, right? That's the second function. Right? 1 times the derivative of this times that. That's that. So that gives you 1 plus log x. Strange but true. Now, what if I had been really mean to you and said do d by dx of the log of x raised to the x? Oh, goodness, that's ugly. X raised to the x power. Can you do that derivative? That's exactly what this is from a rule of logarithm. So yeah, even though that looks really hairy, you say, hey, whoa, we can't do that, can we? Sure we can. First write it like this, because that's exactly that, x times log x, and then go for it. Now that's where, in their thing, they said, well, n is a rational number. I don't think it has to be a rational number. It can be irrational as well. Any real number. Okay. So anyway, that was the same thing. Let's see how they did it. They didn't do that last part because they weren't mean like me. Okay? That would be the first times derivative of the second plus the second times derivative of the first, product rule. And the first is x times derivative of log x is 1 over x plus log x times derivative of x, which is 1. So that's 1 plus log x. Good deal. Make sense? Okay. Here's D. Whoa. What can you do with this? What's that? Okay. Yeah, you're absolutely right. That's the derivative, d by dx, of 3 times the log of x. Is that what you were saying? Okay, but did you put the d by dx in front? I didn't hear that, but I thought maybe that's what you meant. Okay. Because this is something raised to a power, which is the power times the something. Okay. Now, can we do that derivative? What would that be? 3 over x. Perfect. Perfect. Because 3 is just a coefficient, so you don't even have to mess with that. And the derivative of log x is 1 over x. It's 3 over x. Very good. Okay? So we did it. Let's see how they do it. Do I need to leave that a little bit longer? Okay? So that'd be what? 3 okay. I guess this would indicate that the rules don't work here. Okay.
Is it because the ln x is in parentheses?
What's that again?
It says because the ln x is in parentheses.
Yeah, but I thought we took care of that. It was something raised to a power, but I guess that was only true for polynomials. I didn't. So let's go. I would say let's go back to the rule, but let's go back to that thing when they said n was only a rational number, and here, no, it doesn't say that. A and B are positive numbers. Well, log x, no, log x, this is, I guess, then more correct, okay, is do the power rule for the log and then do that. It's a chain rule that, again, I thought the way we did it was right, but it doesn't come out being the same value.
It's a chain rule and a substitution at the same time.
Yeah.
Because that's ln x is u in that case.
What's that?
They're doing a substitution.
Yeah.
And the chain rule, because ln x would be u in this case.
Right, exactly. And yeah, so that's what they're doing. So theirs is right. Like you said, if you do a substitution, let u equal log x, and it'd be 3u squared. Yeah, so that is correct. Sorry. Okay. Kind of, I was going down the same path. Okay. On occasion, let's see, we've still got about more than 5 minutes. On occasion, it is convenient to use logarithms as aids to differentiating non-logarithmic functions. This process is called logarithmic differentiation, which is a really handy tool. I'm just not used to them hitting them this fast. So what if we wanted to find the derivative of that? Ouch. That is a quotient rule with power rules in the numerator and denominator. That really gets to be a pain in the neck, doesn't it? Okay? So what we do here is first take the log of this. Let's first take the log of y. And what would that be? Anybody? Oh, it's been a long time since we did this. Log of a quotient. Oh, and by the way, and they were really clever here, they said x cannot equal 2. You see why, of course, right? Because then you have a 0 in your numerator, you can't take a log of 0. So as long as x is at 2, you can do what we're doing. If you were just doing that and doing other rules, there would be no requirement that x can't be 2. When you're doing the logarithm, you have to do that. So remind me, it's ln of what? What do you say? X minus 2 squared. It's the first part. Minus ln of x squared plus 1 to the 1/2 power. Continue.
2
of x minus 2. And there, I would be tempted to put it in absolute values, but we'll leave it in parentheses, which also includes that x has to be greater than 2. So I would put this, greater than 2. Not just not equal to 2, greater than 2. Okay? But continue. Minus 1/2 the log of x squared plus 1. Okay. So this is log y. Now, off to the side here, I'm going to do something. Derivative of log y, d by dx of log y, is going to be what? Remember that last one that we had? Y prime over y? You remember that? Theorem 5.3, number 2. Remember it? Okay. Now the reason I do that is now I'm going to do d by dx of log y, which would be d by dx of this. Okay, and what would that be? Two over x minus 2, perfect, minus okay, 2x, okay, I'll buy that, over 2 times x squared plus 1. Like the way you did that, now you see those 2's can go out. Okay? They've been dating. Okay. All right. So, we've done d by dx of log y. But you know, that's not really what we're interested in. We're interested in finding y prime, aren't we? But this is y prime over y. And we know what y is. There it is. Right up there. So then our y prime, or dy dx, what do they ask for? Find the derivative of it. Let's just call it y prime. That's easier. Y prime is equal to y, which is x minus 2 squared over the square root of x squared plus 1. Okay? There's that. Times this this derivative we just took here. And it's 2 over x minus 2 minus x over x squared plus 1. Okay. Now that's not particularly pretty, but if you want to see ugly, take the derivative of that. Okay? That will really get ugly. Okay? This is much simpler. Now let's see if they wind up with the same form. I'm going to cheat and look before. You know, we just skipped example 4 and 5, didn't we? I didn't realize that. Okay. Yuck. All right. They did something I wasn't anticipating. I probably should have. They expanded they got this as the 1 fraction. So you're going to have to multiply this numerator by x squared plus 1, and that denominator by x squared plus 1, and multiply this x by x minus 2, and multiply this by x minus 2. So they took it another step here. 2x squared plus 2 minus x squared plus 2x over this product, x minus 2 times x squared plus 1. Okay? And then combining like terms, that gives you a x squared plus 2x plus 2 over x plus 2 times x squared plus 1. Or that's x minus 2. I can't read my writing. Okay. Now, that's what they multiplied by this. Okay, so rather than this part, they multiply it by this. Okay, that goes there. And you notice that one of the x minus 2's can go out. Okay, so their final answer is y prime is equal to x minus 2 over, well, now what you've got in your denominator is square root of this, which is x, this thing to the 1/2 times to the 2/2, so that would be 3/2, x squared plus 1 to the 3/2 power. And this would be times your x squared plus 2x plus 2. That was your numerator here. And I guess they no, they leave it just like that. Thank you very much. You could multiply those out, but they didn't. Okay. So, that actually looks a little better than before. And you would have gotten this had you done all that. What you have to do when you're using logarithmic differentiation, remember that your derivative of the log is your y prime. That's what you're looking for over y. So whatever you get when you take the derivative of this, you have to multiply it by y to give you your y prime. And if possible, simplify it. And I had just written it down, and I didn't take advantage to simplify it. It's not anything wrong, it's just a different form. Now, if you had done it the long way, it would have taken a long time probably to get back to this form, but you could do it. This is a little easier. Now, we've run out of time, haven't we? And the bad news is I skipped right over, without realizing it, examples 4 and 5. So we'll come back and do example 4 next time. Okay? We'll do examples 4 and 5, then remind me that we've already done example 6. Okay? So, remind me of that. All right, homework exercises here, 5.1. Do either 5 or 7, they're both at Calc Chat. 9 or 11, they're both at Calc Chat. In fact, I would do all 4, 9 through 12, but only the answers are at Calc 9 and 11. Any of the odds 13 through 17, they're all at Calc Chat. 17's at Calc View. Do 19, it's both at Calc Chat and Calc View. Any of the odds 21 to 29, they're all at Calc Chat. 23's at Calc View. Any of the odds 31 to 35, they're all at Calc Chat. 31's at Calc View. 37, it should be at Calc Chat, and either 39 or 41 should be at Calc Chat. And then any of the odds 43 to 65. They're all at Calc Chat. 45's at Calc View. And let's stop there and we'll do, well, yeah, stop there. We'll do the rest of them later. Jake, stop there. Don't do those extra ones, okay? All right. Just want to make sure you heard that. All right. Good deal, folks. Thankful. Do I have test for it? Not made out yet. Right. Oh, are you not going to be here Monday?
No, I didn't.
Oh, you just want to get started on it. See, I didn't know how far we'd get today. I'll make it out Monday, guessing how far we'll get Monday.
Did you want me to staple the first?
What's that?
Did you want me to staple the?
Yeah, I'd like. You don't have to staple it. Just, yeah, you can staple it if you want to. It doesn't matter.
Are you
Yeah. payment for the special ed. Huh?
Are you going to drop our lowest test grade?
Yeah.
You are? Thank you.
But that doesn't mean don't do a test.
I got you.
Okay. Because you're going to need the stuff later. I don't want to have to fight with you at council. Okay. Good deal.
So you're gonna give us the test score on Monday?
On Monday.
And we have to turn it in.
By the following Monday. Sooner if possible, but I'll try to be gentle, you know, so it won't be too bad.
Registration for the summer is,
What's that?
registration for the summer.
Yeah, you can do that now.
Well, we have to depend and see how it did in here.
I can't hear,
I
sorry.
said I had to see how I did in here.
Oh, you're going to be
Oh, you know, look at this, we didn't see that.
Yeah.
We just looked up there,
Yeah.
forgot about that.
Yeah, and the only thing I can get on that is that thing in there was not
That's correct, though.
yeah, it is.
Yeah, because see, if we had made this U,
Yes,
that's
exactly.
what we should have done.
That's what we should have done, yeah. And that snuck up and bit me. But I'm trying to think why it wouldn't work with the other one. And I was looking back.
It wasn't in parentheses.
Yeah, but we still. Oh yeah, that's right. I know what you're saying now. We weren't taking the log of that. If we had taken the log of that first, like we're doing now, that would have worked out right. I'm sorry. I just jumped ahead. Good deal. Thank you. More grading to do. Thank you so much. Okay. No, I'd rather do it now than have it all next week.
Some of you 5 days a week, right?
No, actually, we're 4 days in the
4
summer.
days
Yeah.
with every day.
No, actually, long classes. Wait. Now that I think about it, did I go back and change that? No, I started to, but I couldn't get it to work out. No, long classes in the summer. 2 days a week. I hate the way they're doing it in the summertime. I know.
At my age, I'll be a bathroom boy.
Oh, absolutely. Feel free to get up anytime.